Over things once. Yeah, you want to say something? No. It's smiling. It's a very sarcastic expression, isn't it? Things can never be good in the 12th week. So, well, no. I think this is the 13th week. Three, like including this week, we have 3 weeks of classes.
Yeah.
And 1 week of exam. So I guess the comment meant that 13th week cannot. Because I haven't written it down here. I have to post this too. I mean, it's almost, from this point on, I think most of what I do is going to be the same as what I've done in earlier semesters, couple of problem. I don't think I will have time to change it significantly. So the idea probably is we have 3 weeks remaining, 2 weeks I will try to do Kepler problem, that should be possible. The third week, so I have 1 week, I would like to do relativity. And it is usually not sufficient, but in the limited time, I'll try to do as much as possible. Earlier semesters, what I've done is that I have used the exam week to cover a bit of relativity. But I think I'm tending more towards having a proper exam instead of a take-home exam. So that's taking away 1 week in a sense, otherwise I can use that week for covering curriculum. Again, that's something that I can change my mind on. So 2 weeks of Kepler problem and 1 week of relative. Homework should be, I hope to be able to do this in the next few hours. And we will make it due 1 week from today, so that will be 23 Tuesday. The next homework will be 11. We due April 30th. It will again be a Tuesday. That will be the last week of classes, I suppose. And homework 12 has to be, so that's what, third, right? So, yeah, I can make it the next week, but I cannot officially make anything due beyond the working days. So officially it's due here, but then you have the liberty to submit it anytime you want. That's the way I would offer it. Is that okay? And this is recorded, so I'm in trouble. So May 3rd, so this is Friday, and yeah, usual time, reasonable. Exam is on Thursday. Correct? Still, I'm debating. I'm more towards having an exam, but then I'm also tempted to say that, okay, have a take home. That'll be better. How many sets should we take home? All of them.
We have no issues.
Can we make 2 questions in class that this we have done before? Like I think we have 2 questions in class and the rest of, or what I mean is that I think 40% of the grading will be on problems that we do in pass, which will be very short. I think you can ask others, they have done this before. In principle, can be finished in 15 minutes, but you can take the whole 75 minutes out of it. And 60% of the grade will be take home. But the advantage, the bargain is that I cover curriculum. Like the 60% will be a longer homework. It will be like a homework. And I can ask you to look into a video from the past, which helps me cover a content and make a homework on that. So it takes more time to cover, but then it's reasonably, it's easier to score because it's like going through a textbook. Does that clarify, Susan? Is that clear? So that's what I might do, so you both should understand what it is. I think rest of them know what it is because they have experienced it. They have experienced before, yeah. And that also limits my capacity to grade. So that's another, I'm only 40% grade. Right. But 60% is easy to score, so you can surely expect 60 points in the mid if you finish. I mean, there are situations where I can still make a hard grading. Get it get around it. Yeah. Okay, we'll see on that. Let's keep that tentative in a sense. It's a tentative plan that we will have 60% take home and 40% in class, and 40% can be anything from anywhere in the semester. Okay, so that helps you prepare for the course. Okay. We mostly did stationary action principle in this whole course. It's a formalism that gives a lot of insight into Newton's laws of motion. We phrased it in a different way. The idea is stationary action principle. In fact, we even changed the boundary and we learned a lot of what stationary action principle is and how it is describing motion. In fact, when it comes to quantum mechanics, we realized that there is a connection between commutation relations and Poisson brackets, and all this helps a lot. But remember that historically speaking, the major success of Newton's laws of motion was in understanding planetary motion. Kepler had already, before Newton, about maybe 80 years before Newton, given the Kepler's laws of planetary motion. And the major success of Newton was that he could use one equation to explain both how moon goes around the earth and how a stone thrown up in the air falls down a certain distance away. That was a major success, so we should do that problem in terms of course using all the formalism we have gained at this point. But most of what we do in principle, we can start from Newton's equations of motion and also do it. But we will use our Lagrangian formalism, Hamiltonian formalism, and so on. And we should be able to get three things out of it. What are the three Kepler's laws of planetary motion? What are the three laws?
Equal areas.
Yes, so that's second one. So Kepler's. Yeah. 1, 2. Yeah, anything? Yeah, first is that it is the orbit is ellipse, right? Orbit, elliptic orbit if you want. Like elliptic orbit. And second is that as it goes around, so the sun, and basically it also says that it's an elliptic orbit and the sun is at the center, you want to make that correction, any correction on that?
It's at the sun is located next to the center, at the focal point.
At the focal point, that is what Kepler said. But small correction, tiny correction, which is probably not measurable easily.
Measuring the wobble.
Yeah, there will be a wobble, and so what is at the focal point? The center of mass.
Yeah.
Right, the center of mass
Center of mass of your system.
is at the focal point, but the center of mass is so close to the center of the sun because sun is so heavy that it doesn't really change significantly, even for Jupiter. As far as you're in 1% accuracy, that's okay. And the second lot also is that the area, so if you were to take 1 day and wait for a planet to go around, the area, so this is choose any time, we could pick 1 day, for example, and the area it covers, it is the same in any other day. So equal area is covered in equal time, so that's second and third.
T square is AP.
T square equal to
That is AP. Proportional to
proportional to
AP. AQ.
AQ, and what is AQ? What is A?
That's the semi-major axis.
That's a semi-major, very good. So this is AQ. Notice it's an ellipse. Usually when we do undergraduate physics, we presume, even though we say it's an ellipse, most of the derivations are done for circular orbit, and then you say this is the radius of the orbit, but it is a semi-major axis. This was pointed out by one of the students in this class earlier. I was using it wrong earlier. Okay, so we should be able to get these three things, and that was the success of Newton's laws in the early days, that the moment you do this, then you can start predicting the motion of objects, and even to a minute. Like it was possible to predict that at this point, this planet will cross this particular planet. Those were the nice things, that whenever, for example, one of the dramatic things was whenever a planet used to go in front of the sun, like we had a solar eclipse that was moon, but even if a planet goes in front of the sun, you can see a small dot that is moving around across the planet. And you started predicting those things. Earlier, it was just a prediction in the sense of you knew that used to happen, but now you could start predicting within minutes, or at least in hours, it was possible to. In fact, whenever it was delayed by an hour, it was a big embarrassment. Like you had a whole crowd, because it became very popular, exactly like solar eclipse. Imagine we had a total solar eclipse and we advertised that it was at 1:59 p.m. and everyone is watching at 1:59, and it doesn't happen. Right, so exactly like this, as a huge event organized, and if it doesn't happen, it's an embarrassment. So it used to happen in the time of Newton, within few, I think within 40 years, it was possible to predict the transit of Mercury on Sun. And people used to get together like this, and it used to be sometimes delayed by a couple of hours, and it used to be an embarrassment. So that's when you started doing corrections. So how good your calculations are makes your predictions better. So we want to try to reproduce those things. So very broadly, we will call it Kepler problem. I think this was given about, I think approximately 1610, I think 1610 or 10 to 20 maybe. And Newton was born in 1642, so probably at the age of 25, he gave his laws. So 42, 60 to 67, so Newton was probably approximately 1670. When by Newton, I mean Newton's laws of motion. Newton was born in 1642, so I think Newton's laws of motion probably came up in 1670 or so, not sure. Quiz, when did exactly Newton give his Newton's laws of motion the principle, right? So when which year is associated with Newton's laws of motion? I don't remember. Okay. So we would like to talk about two masses. So this is one mass M1, and there is another mass M2. It could be tiny objects like a proton and an electron, or it could be as big as sun and earth. It is good to have a measure of how the masses of sun and earth vary. So we are going to be talking about planets and the sun. What is the mass of sun approximately in kgs? Or if you don't know it in kg, how much bigger is it compared to Mars? Earth? That's always a good thing to remember, which is the dominant player in a field. Is Earth 10 times heavier? Is it equal mass? No. 10 times heavier? 100 times heavier? A billion times heavier?
Mass of sun is
Okay.
332,950 Earth masses.
How much?
332,000 Earth masses.
332
Yeah.
times? Oh, 1,000 you said. Yeah. So it's about, yes,
32,000
that's correct.
times
So
the mass of the Earth.
good. So this is about 10 raised to 30 kgs. That's not like usually. What is good to remember is that there is Jupiter and there is Earth. Earth is about 10 raised to 24 kgs. What you need to remember is that the ratio is a million. So 10 raised to 6 times the Earth's mass is Sun. What that means is that if you want to see the effect of Earth's mass, when Sun is around, you will have to do 6 decimal precision experiment. Right? So it is usually difficult. So it is best to ignore the motion of Sun altogether and pretend that it is only the Earth that is moving in, because Sun is Sun is significant, but it doesn't, the Earth's mass doesn't come into picture, and we will see this. What about Jupiter? This is 10 raised to 27. It's exactly in the center in a sense of order of magnitude. Jupiter is 1,000 times heavier than Earth. Sun is 1,000 times heavier than Jupiter. And so this is about 10 raised to 3 times. This is 10 raised to 3 times. And it's also good to know Moon, and these days also Mars is also very important, right? So this is 10 raised to, I think it's between 22 and 23. So let's say, I think it's 23, probably 10 times, or maybe 100 times, I'm not sure, maybe 22 kg. That might be 100 times heavy. I think it is 100 times heavier because the center of mass of Earth Moon system is not somewhere on outside the Earth, it is inside the Earth, inside the Earth's crust, which means that Earth is significantly heavier. It's about 1/3. So that's approximate numbers. You can get more details. For example, Earth is about how much? Earth is 6 into 10 raised to 24, 5 point. I think, yeah, not sure. Okay, but let's keep that. So these are the two masses, and we can do the same thing for proton and electron, but we are not worried about that. But there is a lot of similarity in the sense Newton tells us that the force between these two masses is along a line connecting the center to center. By center to center, I mean center of mass M1 to the center of mass of M2. This need not be spherical. This could be elongated, but typically they're closely spherical. But whatever it is, there is a point, center of mass inside here, the center of mass. Draw a line connecting them, and there is a force on 2 by 1. It's Newton's law. Force on to, so this is on 2 by 1 is equal to G M1 M2 over let me not say this is the distance r, instead let me say this is the difference in the position vector of these two masses, and then you calculate the distance by the magnitude of this vector and square. Is that clear? And you can also, if you want, say this is Q, and I need to put a direction to this, right? So this is R1 minus R2, so this is R1 minus R2. I can pull out one R1 minus R2, you often write this as R hat is equal to R1 minus R2 divided by R1 minus R2. That's a unit vector in that direction, and often you will see this as R hat times G M1 M2 over so that's it. Newton's laws have three equations or three laws in them. First one pretty much describes what acceleration is. That's almost a definition. Second one, it says that mass times acceleration is equal to forces. And the third, Newton's laws of motion, tells you that it is every action has an equal and opposite reaction. And that's for consistency reason that either you can take both the masses as your system or as single masses. If you take both the masses as your system, then both of them should cancel each other, and that requires the fact that it should be equal and opposite. So we say that there should be an equal and opposite reaction, and that's F1, 2. So that's a force on 1 by 2. And notice Newton gave two important things. One was laws of motion. That's Newton's first law, second law, third law. And this is Newton's law of gravitation. That was an independent concept altogether. He explained gravity, why heavenly objects move. So now, yes.
4 laws. Newton has 4 laws.
Yeah, it has 4 laws, but they are completely different. Yeah, entirely different. Newton's laws of motion is more influential in the sense it is it almost covers everything. You can talk about how electrons move inside until quantum mechanics came and you made corrections, and same thing with heavenly bodies also. Einstein's equations corrected, but for quite some time, like from 1650s to 1900, you had one equation that could pretty much explain most of our understanding in science, or at least there was a promise that it can explain everything in principle. So it was very, very influential, no doubt. Even today, I mean, it's very useful unless you're talking about extremely massive objects like black holes, very close to black holes, or extremely small objects like atoms. Newton's law works. I mean, when you build bridges, it very much works. Yeah. So in that spirit, so that's the equation governing these two equations, and let's write a Lagrangian to this. But before that, I should say, point out that notice this force has this feature that it depends only on the distance between them. It does not, there is no angle dependence in here. So for example, if I place myself at this point 1, and if I'm looking at M2, it is radially at a certain distance on a circle. If I go in here, I won't be able to make out any difference, right? With respect to my coordinate system, I might have changed, but the universe has only one object in there. I won't be able to tell whether it is here or there. Is that clear what I mean? If there are no objects as a reference, I will not be able to make out that rotation. So you say it is angled independent. So this force, if you were to think of it as a magnitude, F21, this is G M1 M2 over R square. There is no angle dependence in here. There is no theta coming in, there is no phi coming in here. So this is theta and phi independent. So theta and phi, it is independent of these. Like if you think of spherical coordinates, there is no theta and phi dependence in this. So these type of forces are called central forces. So Newton's law is Newton's gravitational force is a central force. It is in the direction of R. In fact, it is in the minus R. If you were to say this is 1 and this is 2, it is radially inward. So, but I chose it so that R1 minus R2 is in the opposite direction. So, if you're thinking of the spherical coordinate, then it is minus R hat. But here R hat is equal to R1 minus R2. Or in the direction of R1 minus R2. Central forces, the basic idea is that it is theta and phi independent, and we'll try to make this more concrete. I will give a vector equation for that as we proceed. We saw that already whenever there is spherical symmetry, how do you say this is angle independent? How do you check if a function is angle independent, angle and phi independent? Dot product of what? Yeah, that's the force dotted with. But what we are saying is the magnitude should be independent of theta and phi, right? Yes, that's also necessary. So how will you write this as an equation instead of saying that it is theta and phi independent? How do you check it? Like you saw that in one of the homeworks. Like angular momentum, no, we said, yeah, angular momentum, right? Rotation. If it is rotation and it is invariant under rotations, what's the operation that comes into picture?
The cross product
Cross product, yes, of
of the two vectors there. If the two vectors are the same, then there's no angle involved.
yeah, but this is not at this point. This is, I mean, yeah, but F is a vector, so
Delta,
huh?
delta.
Delta,
Delta.
delta theta. Remind me. Delta theta. Maybe you're right, but I'm trying to remember what is delta.
With cross product with delta theta. Or delta small.
Oh, small angle. No, yes, in a sense, but there is a lot of connection between them. I think it's but simpler. So you say this is instead of saying this, you would say R hat, or let's say R, doesn't matter. This is now, I should be careful, right? Let me change this definition to R12. So that now I have R as the spherical coordinate R hat, right? So I changed this to R12 here. So now R is no more whatever I said earlier. So R crossed with F, the force, right? That seems to be just a cross product, but notice the force is equal to the gradient, and we have been writing gradient as d by dr, right? Not a common thing. And what would be here? Force is equal to negative gradient of potential energy. Very good, right? So we have to have a potential energy associated with this force. Gravitational force is conservative, so there is a potential energy associated with it. And if this is equal to 0, then it is theta and phi independent, and we showed that in your homework. I mean, we can quickly do this. It's good to have a feel for it. So R cross gradient. Right, this is equal to r crossed with gradient in spherical coordinates. Anyone remembers?
R hat,
R hat,
about
good,
theta hat 1 over R, about theta.
very good. And
Y hat,
R sin theta.
1 over
very good,
R sin theta.
very good. Right? So R crossed with this will kill this term. R crossed with R hat is 0. So this is 0. Plus R crossed with theta is in the phi hat direction. So R cancels out. So this is phi hat times d by d theta. And R crossed with phi hat will be minus theta hat, right? And there will be a sine theta that will cancel out. So minus theta hat d by d phi. The R crossed with will have this R sine theta in it. I think that came in your exam also. I think that was exploited in that exam problem. But now if you want this to be 0, this has to be applying on. So what is it saying is that phi hat d by d theta minus theta hat d by d phi of u is equal to 0. So if this is equal to 0, so that's u, and that u, if that is equal to 0, that's what this means. If you have a vector that is 0, its components should be 0. So that's equal to 0, and that's what we were talking about, right? This is theta and phi independent. So if you want to write it in an equation form, what this means if you want to check with any force, given a force, is this a central force or not? So you immediately do this. If R cross F is equal to 0, that means it's a central force. By central force, it means that it is angle theta independent, angle phi independent. But again, intuitively, there is no replacement for it. We have an intuition for what it means by theta and phi independence. Okay. So that's our force. We have two masses. We would like to write a Lagrangian. We would like to write the equations of motions for that, and then solve the equations of motion. And the expectation is that that equation for the orbit will be an ellipse. In fact, it is not always an ellipse. What are the other orbits that an object can have? Kepler, of course, said that it has to be elliptic. Does it always have to be elliptic? What are the other possibilities?
Could be circular.
Could be circular, very good. And yeah, it can be hyperbolic comets,
Hyperbolic.
like not the comets that come periodically. Those are again long ellipses, very eccentric ellipses. But sometimes we have comets that comes once. Like it comes from infinity, comes to Earth, and then goes back, and that's the end of it, right? That's hyperbolic. So it only comes once, right? That's a hyperbolic path. And there is one more solution, and that is parabolic. It can also be parabolic, but parabolic and circular are, it has to be perfectly,
Has to be like
it has to happen in a perfect sense. It has to be a lot of fine tuning has to be there. So most of the time it is either an elliptic orbit or a hyperbolic, or even hyperbolic orbits are not common. If it is hyperbolic orbit, you can be pretty sure that it is not part of the solar system, because it is coming from somewhere else and going somewhere else, right? So that is not most probably part of our solar system. In fact, most of what happens in our solar system, we will see because of angular momentum conservation, happens in a plane. Like if the comet comes in the plane and goes in the plane, then most probably it is part of the solar system. But if it is coming from outside, there is no restriction. It can come from the top. So this is the plane of our solar system. It can come from the top, come to the sun, and then go away. And sometimes it can also get trapped. But whenever it is off this orbit, off this plane, it's a good indication that it is not part of the solar system, it is coming from somewhere else, it's a foreign body in a sense. How do we see this in the sky? In the sky, this plane, the plane of the solar system, is pretty much the equatorial belt. That means anything that rises from the sun. And at 12 o'clock in the noon, right when it goes up, if the orbit is like this, that means it's part of the solar system, most probably, not necessarily, the stars are not. Okay. So anything that is part of our solar system will be around the equatorial belt. The angle you can have is about 11 degrees up and down, because sun goes 11 degrees in the winter to the north and 11 degrees to the south in the summer. So that much stretch you have. Most of our solar, most of the planets that you see will be in that belt, if you stand on the equator. If you're away from it, then they go down and so on. So it is called the equatorial belt of the sky. It is good to realize that that's that. And look it up, it's kind of nice. I think have I mentioned about the sun? Since we had a solar system, you should, like, if you, how many of you drive? Most of you don't, right? You drive, you drive, I think you're walking, right? Probably you guys walk, right? Try to pick a east-west direction for at least 30 seconds of your walk, right? Or at least look. I mean, you don't have to be walking, right? Look. Okay, I'm just continuing. It's just continuing. Okay. Thank you. Okay, so what I will just quickly say this, so you pick a east direction or west direction, doesn't matter. So this is the east west, usually you draw it the other way, then, so let me be with that notation, so. That's east, that's your west. Stand somewhere on a road around that, it's usually the direction you have to pick, that much price you have to pay, but again. In US, most of the roads are aligned with east-west, so it's very easy. In many places, it's not, that luxury is not there, so that your coordinate system is built for you, so that's very easy. So you stand here, every day, if you look, March 21st is the day of equinox, are you aware of that, March 21st? The sun will exactly rise on the road. If you're at 6 o'clock, it will be right on the center of the road, or east setting and rising. As you go into the winter, this sun will go here, 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 then stop and come back. And then go this, so this. Is that clear what I said? So the position of the sun at pick a time, it doesn't matter, 6 o'clock, 7 o'clock. It'll be right dot on the road. As it gets winter, it'll go to the. As it gets in the winter, it goes to the south, sorry. Okay. In the winter, it goes to the south, and in the summer, it goes to the north. Okay, and this happens on July, this will be on June 21st. This is March 21st, and this is December 21st. Actually, most of.
Also September 20th.
Isn't, yeah, September 21st, again, it goes crosses this, yes, that's correct. Good thing to just observe, like on a daily basis, you can do this, or look for the sunlight, like all of us like sunlight. in the morning it comes, like pick your window of choice. You will notice that in some of the months in the morning, sun is coming this way. And on the other half of the year, sun is coming the other way. And if you're really smart, this happened with me, like not, April Henley, who is, who teaches astronomy here. So I went to Norway. I used to go to Norway every summer, in the past. And what used to happen is Norway is very special in the sense the days get really long in the summer and, very short in the, in the winter. So I had gone in the summer and she knew this. So we were having a video call, between us. And based on the shadows that was forming in the room, she exactly told me which side I was facing, which direction of the room I was facing, and so on. So you can tell a lot of things just based on, the position of the sun, and, if you know exactly, maybe the position that you have. So it's kind of
That's what-
interesting things you can conclude from that.
Go about the rim too.
Yes, yes. And no wonder we depended on this a lot when we were traveling, right? In the past, we didn't have a GPS, so we used to use this, for travel. Okay, all that. To clarify that we are doing planetary motion, it's interesting. It should be, if not anything for curiosity, it's, good to, study these things. And let's write down the Lagrangian. If you have the, so potential energy for, gravity, and I should move this, right? Like that. Yeah, so that's a force, right? Does every force have a potential energy associated with it? No,
No,
only conservative forces. This is a conservative force. How will you check that? You can't do. So conservative,
F equals minus the gradient of.
how will you do that? How will you check a force is conservative or not?
Usually conservative forces have.
What is the work done by a force? Huh? Path independent. Work done should be path independent.
If it's a
So if you
closed-
go from point A to point B, it doesn't matter where it, or you say that the curve, if you go around in a circle, or it doesn't have to be a circle, around a closed loop, the work done is 0. Which is equivalent to saying curl of the force
Equal to 0.
should be equal to 0. So let's check that, like that should be possible, so let's write this as. It is good to write this force as, G M1 M2 times R hat. Let me write vector R by R cube. Right, some constant times vector R by R cube, and curl of that will require curl of R over R cube. What is that equal to? So there are two places that it can, hit. So this is curl of R over R cube, or I can have R is sitting, so that is, let me put the R here crossed, and that is the gradient operator hitting on 1 over R cube. Right, the gradient operator can hit on this or on the cube, right? When it hits on R, there is a curl of R there, and that is, R cube in here. So think of this as a gradient. If we don't have the operation in between, what is this equal to? This is 1. So that's equal to 1, and then we are taking the curl of that. This is a symmetric object, curl is antisymmetric. You can argue that way that this will be equal to 0, or this is epsilon ijk times delta, jk. there is a antisymmetric piece, there is a symmetric piece, so that will always be equal to 0. So this is equal to 0 plus this term here, that is 1 over r cube, again, do this, so this is minus 3 over 1 over r raised to 4 times the gradient of r times vector r. What is gradient of r? The magnitude, that is r hat, very good. And that gives you, so this is 0 minus 3 r hat crossed with vector r over r raised to 4. Vector r hat crossed with r is again 0, so that's equal to 0, right? So the curl of the force is equal to 0 means it is conservative. And why is that? How is that related with the work done idea? If you have work done, this is force dotted with dl along a closed loop is equal to 0. How is this and this connected? If you have a loop integral, what happens?
Is,
Well done.
yeah, that's.
Now that's the work done by a force along a loop, right? So you start from here, you go around, take a full turn and then come back. That's a work done by a loop. But how do I go from here to del cross f is equal to 0?
So it is.
Stokes theorem, very good. So the Stokes theorem tells you that this is del crossed with f, very good. Multiplied by an area is equal to 0. This time you don't have to do a loop, this is on a surface. And if that has to be equal to 0, del cross f has to be equal to 0. So all that tells you that as a if it's a conservative force, the work done along a closed loop is equal to 0. It is path independent, you can say it in that terms, or the curl of the force is 0. All that means that there is a potential energy associated with this, right? If you have a conservative force, there is a potential energy. And what is the potential energy associated with this force? So you can write it as a grade, so force can be written as a negative gradient of potential energy, and U is, so what is the energy that gives you this force? So gradient of what function gives you this?
EN1 into over R.
Very good, that's what you learned. That's the potential of a charge or a mass. So this is usually we say R, but let's write this as R1 minus R2. Like introductory level physics, we don't try to emphasize this R1 minus R2 so much. We just say that's the distance between the two masses, and there is something missing there. Huh? Direction, no, right? Potential energy scalar. Negative, right? It's attractive. So for gravity, it is negative. If you were doing electrostatics, electron and the proton, that is positive, right? So that's your potential energy. Once you have potential energy, we can write down the Lagrangian. Right, Lagrangian is kinetic energy plus, no, not the plus, right? Minus the potential energy, right? First of all, what are the coordinates that it will depend on? Lagrangian depends on coordinates, correct? First, you have to decide on that. It depends on the coordinates of the first mass and the coordinates of the second mass, then the velocity of the first mass and the velocity of the second mass. And maybe there is a time dependence in there, but time dependence will not, let me write that down, but it will not be there in a minute. I will show this. Kinetic energy of the first mass is half m1 v1 square, right? So this is v1 and that's v2. So that's half m1 v1 square. The second mass is half m2 v2 square and minus the potential energy, But potential energy already has a minus sign, so it's plus of G M1, M2 over R1 is R2. Good. Is there a time dependence in this? No. So immediately we see that, oh, this is no time dependence in there. So that's one. So immediately we have Lagrangian. We can write down the equations of motion. So let's write that down for a moment, but we are not going to use this. We are going to change this significantly. But let's so that the moment you have a Lagrangian, you will first get the canonical momentum with respect to the first variable. That will be equal to dl by dv1, right? There is no velocity dependence in here, so it is simply m1 v1. p2 is l by dv2, that's equal to m2 v2. And we can also do, so the force, so there will be a force onto one, so let's just do this as partial derivative of L with respect to R1. That's what turns out to be the force on one by two in a sense. So this is equal. So now I have to take the gradient with respect to R, so it's in the denominator, so it is minus G M1 M2 over R1 minus R2. And then you take a square of this, and then I have to take the derivative of this magnitude. So this is the magnitude. So this is R1 of R1 minus R2. And the magnitude. Remember gradient, so this is like a gradient of a vector R, right? So this is the magnitude, and this is the gradient operator associated with this. You would say there is no R1 minus R2, I can always put an R1 minus R2 and this will work out the same. So this is equal to R hat. Right, so that's the R hat showing up, and this we will write this as minus G M1 M2 over R1 minus R2. Write it as Q, and this is in the direction of R1. So R2. So now it's okay. And the same idea goes through it here. So dL by dR2 is equal to minus G M1 M2 over R1 minus R2 square. This time it is d by dR2 of R1 minus R2. And that's equal to, except for a sign, these two are exactly the same. So this will be plus. Or we can flip this, right? Keep this minus, and this is R2 minus. So Lagrangian equations of motion is that d by dt of P1, right? P1 is M1 V1, which is M1 second derivative of R with respect to time is equal to minus G M1 M2 R1. Q, and the same thing for the second coordinate.
Like,
Oh,
when you take the Lagrangian with respect to dr1, wouldn't that be just wouldn't that just be equal to just r1? I mean, g in one, g times in two, and then over r1 minus r2 squared times r1,
Yeah,
r2,
this one,
yeah,
this equation,
yeah, the next one. It's over one more,
yeah.
yeah,
So how do I get this? So this point here, this is R1 times R1 minus R2, right? Is that efficient? How do I evaluate that?
yeah, wouldn't that be just minus r2?
Oh, because this does not depend on R1, right? So the idea is that this is the same, or d by d R1 is the same as d by d R1 minus R2. You can substitute if you want, let's say capital R is equal to R1 minus R2. Then, so wherever I see R1 minus R2, I write this. So what is d by dr? D by dr will be equal to d dr1 minus r2 with respect to dr, and then d by dr1 minus r2. Does that help? Right.
Yeah,
And so this is just one if you want, and maybe the colors kind of motivate this. And my main point here is that this is the same as the R vector without the vector and vector R. Did I help? Did that help? Probably not. I think maybe,
yeah, I think okay, now that becomes one.
yeah, let me try this better, okay? Give me a few minutes. I'm going to make that transformation anyway here in a few minutes. I'm going to change the coordinates in a minute. So we will see this again. At this point, let's say that this is equal to R1 minus R2 divided by R1 minus R3 magnitude. Okay. Let's I will be doing this again, so even if you're confused, just follow it down. Okay. So this is equal to G M1 M2 and R2 minus R1 over R1 minus R2 cube. Okay. This is nothing but Newton's laws, right? If you did not know anything about Lagrangian or anything, this is how you would have begun. Right, mass times acceleration is equal to the force in if you're a planet, the only force is the one that you experience from the sun. There is no other force, and this is the force that's a reaction force in a sense. Okay. In Lagrangian, we try to change coordinates, correct? We always pick the right coordinates, and there is a huge simplification in here. Let's do the same thing here, and we will see this transformation coming in. And the main idea here is that the potential energy depends on R1 minus R2 alone. Right? In fact, in introductory level physics, we already use it. We say that it is R. Right? We never bother to write this R1 minus R2. So it is good to start with that. So let's introduce a new coordinate, R, which is R1 minus R2. And we also know, based on experience in introductory level physics, that center of mass plays an important role. At this point, it is just a transformation, but the motivation is the center of mass. So what is the center of mass of two objects? So if I have, so what will be the center of mass of this system? Yeah. So the center of mass of the system, let's call it R. How will you define that?
M1 in half divided by M1 percent.
Good, so very good. So it is M1, R1, weighted average, right? So plus M2, R2 divided by M1 plus M2, I'm going to write on the left. So the idea is that you are working in R1 and R2 here. Change the coordinates to R and capital R. So everything that we did here, we'll redo it in terms of these coordinates. And there we will see this again, this operation will come up again, and then it will get clearer that why that works out. Okay. So if that is the case, the potential energy is the easiest, right? Potential energy U, which was equal to G M1 M2 minus G M1 M2 over R1 minus R2. In the new coordinates, it's very simple. It is G M1 M2 over R. Right? So that's the easiest. But now there is kinetic energy. Let's start with half V1 M1 V1 square. So kinetic energy of, let me write that K1 is half M1 V1 square. That's R1, right? So I have to solve for R1 out of this. So this is having R1 in here. So this is half M1 D vector R1 with respect to time square. I have to solve for R1. How do I solve for R1? Consider this as linear equations. So R1 is equal to, I have to add, right? So I have to get rid of R2. So I multiply by M2 in the first equation and then add them. If I multiply by M2, I get a minus M2 R2. Add that to M2 R2, that goes away. I get an M1 plus M2 R1, so I have to divide that out. So this is equal to vector R plus M2 over M1 plus M2 times vector R, right? I did it in my head, but you can check that, right? So basically, I multiply by M2, add them, these two goes away. So that's vector R or M2 vector R plus this, then I have to divide by M1 plus M2. Right? So that's what you get. Do the same thing with R2. With R2, I have to subtract this, no, the first equation from the second equation, but after multiplying M1, right? So it is, as I'm subtracting the first from the second, so it is R, and it will be minus of M1 over M1 plus M2, I think. Check me if I'm wrong, let me know, okay? A good check is, if I do R1 minus R2, right? These two cancel out. These two add up, so M1 plus M2 adds up, so that gives you this, right? And this one, second equation is how to check. Is that easy? Yeah, multiply by M1 and M2, because then these two cancel out immediately. Yeah, M1 and M2, and then you add, that works out too. So I think that's correct. So dr by dt, you have to take the derivative there. So the kinetic energy K1 here is equal to half M1 of dr by dt plus M2 over M1 plus M2 times vector dr by dt squared. It's equal to half M1 times capital dr by dt squared plus, that is a square of this, so it is half M1, M2 square divided by M1 plus M2 square and dr by dt. And there is this cross term, so it is 1 by 2 M1 times 2 times M2 over M1 plus M2 by dt dotted dr by dt. It seems like we are complicating. That doesn't seem to be simplification, but there will be simplification, significant simplification. K2 similarly, the only difference is that this will be minus. Right? K2 will be minus, and that's the main simplification. This will be M2 capital dr by dt square. Good. This will be a minus sign, so plus 1 by 2 M1 square M2 divided by 1 plus M2 by dt square minus of M1 2. Okay, if I add these two quantities, so my Lagrangian now becomes, so Lagrangian is equal to K1 plus K2 minus U, right? So if I add those two quantities and put the U also, you have half M1 plus M2 times, let me call this velocity capital V square. V here is dr by dt. Capital V square, and the small dr by dt. When I add them, there is a M1 plus M2 square. When I add them, there is M1 plus M2 that comes out, and what I have is M1, M2 over M1 plus M2. The one of the M1 plus M2, the denominator goes away, and this is dr by dt. Let me not use this. Why? Let it be explicit. And this is plus, right? Plus, because U is minus, so it is G M1 M2 over R. Notice what my Lagrangian depends on now. The Lagrangian is expected to depend on capital R, small r, dr by dt, and small dr by dt. That's the expectation. But the nice part is that it does not depend on the center of mass. The interaction does not depend on the center of mass. There is no R showing up here. So this is not there. Which means that the momentum associated with it will be conserved. Like if you, the momentum associated with the velocity of the center of mass will be conserved. Also notice that the R dependence is purely in the form of R. This is purely in the magnitude. There is no angle associated with it. So there is more simplification in there. But let's keep this. In the last few minutes, let me get the equations of motions associated with that. I think we can do that. in L R small r, this doesn't exist. R by dt and R by dt is equal to half. Let me introduce two masses. Capital M is equal to M1 plus M2. Plus half mu, I'll define mu as 1 over M1 plus 1 over M2. This is called the reduced mass of the system. So this becomes mu times d r by dt square minus g M1 M2 plus r. Okay. Let's do P associated with R. That's equal to L with respect to R dot, let's say. That's equal to M times the R by dt. The canonical momentum with respect to the small r, R dot, that's equal to mu times dr by dt. The force, the L by the R, that's equal to 0. There is no force acting on the center of mass. The center of mass just drifts, right? That's a significant simplification that comes in, and the L by R, that's equal to d by dr of 1 over r of, let me just write that down, that's straightforward. So that's minus r hat g m1 m2 over r squared. So we have equations of motion, d by dt of m Kepler is equal to 0. That implies that dr by dt is equal to a constant. Whatever its center of mass of velocity is, it keeps itself constant, and mu times second derivative of r with respect to time square is equal to minus r hat g m1 m2 over r square. Still not a significant development. This is what we introduced in introductory level physics. The only difference we have introduced is that this is now mu. Right, this is a reduced. So there's a small correction we have introduced, but if it is sun, it's a million times bigger. So yeah, quiz, actually, that's a good thing. So quiz, right? For sun plus earth, find mu. Okay, that should be very insightful. Like, what is the reduced mass of the sun plus earth system? Remember, earth is 10 raised to 6 times smaller than the sun. Okay, so let's say find mu to 2 sig digits. Let's make it even 4 sig digits. And try to have an understanding of that. It's a very straightforward, but still, it should give you an idea of how sun, how much wrong is introductory level physics. So, like when we do introductory level physics, we write, what do we write here, by the way?
Let's just,
In introductory, which mass is this?
let's use the mass of the larger object.
So if we are doing sun earth system, is this mass of sun or mass of earth? There are only two masses.
No, it'll be the earth, it'll be the Earth's mass because the earth is what's moving.
It's the Earth's mass that is, so reduced
Sun's
mass
not
that
like
you
moving,
calculate,
though, it is.
even though sun is dominant. It is inverse, right? So the bigger one goes away. So this will come out to be the Earth, so that's what you want to check out here, right? You want to show that that really is the case. Okay, I'll stop here. Lost too much.